All right, as a reminder, as we get into the selected homework problems video, you don't have to watch this all at once. Did I mention that at the beginning of the last video too? Look at a problem, I'll go over it, take a break, work on some more problems, then look at the next problem as well. Theodore is saying hi. He really likes that corner, but apparently he's on the other side of the chair today. Let's get to it, all right? This is a very catty section. We're going to start by doing number 206 from the textbook. Textbook. I don't think anyone talks like that. Maybe theater people do. Analyze the graphs of f prime. So notice this is the graph of f prime, not the graph of f. And list all intervals where the original function is increasing and decreasing, and the minima and maxima are located. And again, the book is a little... The book is a little inconsistent about whether it says this function is going on forever or this function ends. I'll accept either interpretation here. I'm going to assume that the function ends because that's what it looks like to me. So let's see. Where's f increasing and decreasing? F is increasing on the intervals where the derivative is positive. Increasing means it's going up. Going up means positive slope. So where's the derivative positive? And again, this is where it really matters that we're looking at the derivative. This is the derivative. Where's that derivative positive? Here, let's zoom in. Where's the derivative positive? Well, it's positive between -1 and 0. And from 0 to whatever this is. Let's say positive 0.6. Yeah, the first interval is definitely -1 to 0. The value of this slope function is positive. We don't include either endpoints. We have an open interval here. They're not included because the derivative is equal to 0 at those endpoints. And then the derivative is also positive from 0 to, let's say this is like about 0.6. So it's also positive over here. And again, small thing, 0 is not included, so we do have to write it like this, as two disjoint intervals. And we can basically do the same thing for decreasing. F is decreasing when the first derivative is negative. Well, this is where this shows us our first derivative, and the first derivative is only negative in this portion of the graph between -2 and -1. Lots of open intervals here. It also wants us to tell where the local minima and local maxima are located. So remember that you have a local minimum when it goes from decreasing to increasing. And you have a local max when it goes from increasing to decreasing. So we can just kind of go backwards and make a little sketch here. Right, if this is -2, and this is -1, and this is 0, and this is like 0.6, we know that the function is increasing on this interval and on this interval. We know the function is decreasing in this chunk. So we know that f prime at -1 equals 0, and it goes from decreasing to increasing, so local minimum. We don't know the actual function value. We only know that there's a local minimum when x is equal to -1. When x is equal to 0, that's also a critical point. But the first derivative test says that there's no local extremum here because it's increasing and then increasing again. Kind of have like this situation or something. And that's it. That's it for this problem. That's all we know. That's how you approach these sorts. Do 214. Scroll down to 214. Wait, what are we supposed to do for this problem? Analyze the graphs of f prime, list all inflection points and intervals that the original function is concave up and concave down. Okay, so find where it's concave up and concave down, and inflection points. So remember, a couple definitions of concave up. Concave up is when the second derivative is positive, but that doesn't help us here. We only have a graph of the first derivative. What was the other derivative for concave up? The other derivative was when f prime is increasing. So we're going to have to use that derivative, that definition here. When is f prime increasing? When is f prime going up? Well, this is our graph of f prime. F prime is going up, going up, going up, going up. F prime is now going down, going down, going down. And then f prime is going up and going up and going up again. So it's concave up when f prime is increasing. So we're going to say it's concave up on the intervals. Well, let's say negative 0.6 up to 0. On that interval, f prime is increasing. And from 1 to 1.5. Similarly, it's concave down when f prime is decreasing to the original function. Again, we're talking about the original function, which we don't know what it looks like. Talk about how to find that in Calc 2. The original function is concave down from 0 to 1 because the first derivative, which we do know, is decreasing on that interval. So that's one of the kind of weird things is you say, Jason, concave up, you talked about parabolas, but we're not talking about whether f prime is concave up. We're talking about is f concave up. Connecting all the little bits and pieces here. And lastly, points of inflection is when the concavity changes, as long as the second derivative is continuous, which it is. We know the second derivative is continuous here because the first derivative is very smooth. That's not something we got into too much, but it's not really something I want you to worry about unless I targeted that question specifically. So point of inflection. Again, we don't know the y coordinate. We don't know the original function, but there's going to be a point of inflection when we change from concave up to concave down, when x is equal to 0 and when x is equal to 1. I really like boxing in gold. And yeah, I'm going to say gold for the rest of this class. It's yellow. But it makes it feel special. I think that's everything that asked us to do, right? Analyze the graphs, list all inflection points and intervals that it's concave up and concave down. Analyze the graph. That's just telling you what to do what we did. Let's do 238 next. Oh, that's a lot of parts. So this is just doing what we did at the end of the last video. I'm doing another one for you guys because I know people are not going to like this one. All right. Increasing, decreasing, local extrema, concave up, concave down, inflection points, sketch the curve. We're just doing all of that last example. That was example 5. We're just doing it all again for 242. Oh, wait. No, we're not. Just kidding. I'm not doing that again. I said I was going to do it again to be nice to you, but I'm not. We can talk more about those ones if you have questions. Once was enough. 242 is the plan. We'll go stick with that. Interpret the sentences in terms of f F prime, and F double prime. I'm going to type these ones out. The 242 says a bike accelerates faster, but a car goes. I'm this close to taking this. I might cut the whole video and take this off of the homework problem. All right. A bike accelerates faster than the car. So the acceleration of the bike is bigger than the acceleration of the car. Let's write that down, okay? This is going to be fine. This is fine. I can't. I'm having issues over here. What is going on? So the acceleration of the bike is more than the acceleration of the car. What is this program? Why does it think I want to type that way? Also, how do you spell of? Not like that. So let's just rephrase the original problem because this is the way the problem is phrased is bad. A bike is accelerating faster than the car, but the car is going faster than the bike. So two things. One's acceleration, one's velocity. And here F is the bike's position minus the car's position. And we'll assume everything's positive here. Okay. So F is the bike's position minus the car's position. If you want to think about these in math, you can think about it as something minus something else. So let's start with this. Let's interpret this a little bit. And then we'll talk. We have to figure out what the heck the problem's talking about before we can even do what it wants. So if the bike's position minus the car's position is F, well, that means that F prime, right, is the bike's velocity minus the car's velocity. And F double prime, right, is bike's acceleration minus the car's acceleration. So we have to use this information with these two sentences. So the acceleration of the bike is bigger than the acceleration of the car. So the first thing is bigger than the second thing. So if they're both positive, that tells us that F double prime is positive. The car is going faster than the bike means the car's velocity is bigger than the bike's velocity. So if the car's velocity is bigger, then small minus big is negative. So that's just kind of I don't even know. What is this problem asking? This is just connecting all of the parts of the problem. What does it want as our answer? Interpret the sentences in terms of F, F prime, and F double prime. Oh, I like these problems. I'll do another one. These are good. I lost my mind just because of the wording. I just really hate the wording of the start of 242. A bike accelerates faster than the car does, but a car goes faster. That just means, and this is our final answer, that F prime is positive and F double prime is positive and F single prime is negative. That's what it wants you for these answers. It just wants you to interpret these sentences into math. Oh, I'm going to do another one, bonus one. This doesn't take that long and they're pretty cool. And hopefully it'll be helpful to do another one. Let's do 244. I'll make a note to myself. Wait, I skipped 238. Wait, we are going to do another one of these. We are going to do 238. Yeah, I did. We are going to do another one of those really long ones. I don't know what's wrong with me, guys. We'll be out of order. 244. Stock prices are at their peak. So F is stock price. and they're at their peak. Stock price is at the peak. So what does this say about F, F prime, and F double prime? Actually, there might be a little bit more. What can we say about F? We made comments about F double prime and F prime. I don't think we can say anything about F though. Yeah, we don't. In this last one we couldn't say anything about F, but in this new one we can say something about all of them. Yeah, this is 242. So that means local max of F here, which means that F prime goes from positive to negative. The function goes from increasing to decreasing. And F double prime is negative. We're concave down, assuming that this is a nice enough function. All right, local max, positive, negative, concave down. It's ironic that we're assuming that this is a nice function in order to answer the question, because stock prices really are a great example of not nice functions. And in fact, a lot of times stock prices are related to something called Brownian motion, which is a really is a field called stochastic calculus. And in calculus is like a first year math major, sciencey type of class in college for a lot of people, maybe second year, depending on how you're doing it. Stochastic calculus is like very high graduate level math. So yeah, we'll assume it's nice. We're not going to worry about stochastic calculus here. All right, let's finish this video with that 238, with that super long problem. Let's just go. Basically, this problem is asking us to analyze everything in this section for ln x square root of x. On the interval from 0 to infinity. Because this is the only interval where this function is defined. All right, let's start with increasing and decreasing. How do we find whether it's increasing or decreasing? We look at the derivative. So f prime, the derivative, what is our function? This is such a nasty problem. What is our function? Our function is one function times another function. Oh, it's not as bad. It's not as bad. It's not as bad, maybe. We're going to have to use the product rule. F of x equals the natural log of x. F prime of x is 1 over x. G of x equals x to the 1/2. G prime of x is 1/2, x to the negative 1/2. Product rule says derivative of the first times the second plus the first times the derivative of the second. And we can clean this up a little bit. Right? X to the negative 1. Right? This is x to the negative 1 times x to the 1/2. Add the exponents, you're going to get x to the negative 1/2. Plus 1/2 natural log of x times x to the negative 1/2. This is the form with rational exponents, but you may prefer this form, 1 over root x plus ln x over 2 root x. So both of these are good derivatives. One form is nicer sometimes, the other form is nicer other times. We'll eventually have to take the second derivative, which will include the product rule again. So where is this increasing and decreasing? We have to use the quotient rule. Whoa, no. We're going to find critical points. All right, so we're curious about increasing and decreasing. Now let's find the critical points. So critical points are when the derivative equals 0 or is undefined. Natural log is undefined for 0 or negative values. Square root of x is undefined for negative values. And when x is 0, we're dividing by 0. Luckily, none of those are in the domain. So this derivative is actually defined for all points in the domain. So we only have to look out for when the derivative equals 0. And we'll solve this by multiplying both sides of the equation by the LCD, which is 2 root x. Similar to the problem we did in the earlier videos here. We'll distribute that on the right-hand side as well. The square root of x's cancel in the first term to just leave us with 2. And everything cancels for the second term. Ah, this is not too bad. When is the natural log of x equal to negative 2? I think my cat just farted. Convert it to exponential form. This is in logarithmic form. That's going to be when x equals e to the negative 2. Or you can approximate it. This is our only critical point. Yes! Messy function, but at least not a lot of critical points. So, draw a number line. E to the negative 2. Since our derivative function is continuous on its domain, the only time the derivative can switch signs is when the derivative equals 0. So everything in this interval will be the same sign, and everything in this interval will also be the same sign. Let's look at the sign of the derivative. That tells us whether the function is increasing or decreasing. So again, you might want to find out what e to the negative 2 is, or you can just plug in something really, really small. I know that something really, really small is going to be in that interval. So plug that in into our original function. I'm going to use a calculator. We'll use Desmos. Let's have f be, sorry, not into the original function, plug it into the derivative. Our function is ln x times the square root of x. Our derivative, oh, it's really grumpy about this. That's what I thought. Our derivative, oh wait, hold on. I don't want to show this. I don't want spoilers. Our derivative is 1 over the square root of x plus ln x over 2 root x. And again, no spoilers. We want to know what is the value of the derivative using a calculator when x is very small. It's going to be negative. So it's negative everywhere on this interval, which means it's going to be decreasing everywhere on this interval. What is the value of the derivative to the right of e to the negative 2? And again, if you don't feel like calculating what e to the negative 2 is, you can just pick a number that's pretty big. F prime of 10 is a positive number. It means everywhere in this interval, our original function is increasing. So we know that our function is decreasing on the interval from 0 to e to the negative 2. And it's increasing on the interval e to the negative 2 to positive infinity. And again, it's okay if you want to use a decimal approximation for e to the negative 2, unless I specify one way or the other. Okay, that was part A. Part B was local extrema. We basically already did it with the first derivative test. Right? We have a critical point right here, and it goes from decreasing to increase. So part B really is just saying that there's a local minimum at whatever the function value is. Or sorry, local minimum of whatever the function value is at x equals e to the negative 2. What's our original function value at e to the negative 2? It's about negative 0.7357. Or again, if I'm using exact values, let's go hard on the exact values. Go off to the side, right? F of x equals ln x square root of x, I believe. We do it by hand. And we get ln of e to the negative 2 times the square root of e to the negative 2. Square root is an exponent of 1/2. Ln of e to the negative 2, ln and e are inverse functions. They cancel. We get negative 2. And then multiply the exponents on the other one, so it's negative 2 times e to the negative 1. But you can also get the decimal approximation here. That's our answer for part B. Part C is asking about concavity. So to get concavity, we're going to have to look at the second derivative. Remember that the first derivative, we said, was 1 over square root of x plus ln x over 2 root x. And then we also had said that we might want it in the other form. And we will definitely want it in the other form to take the second derivative. So, second derivative, use the power rule, negative 1/2, x to the negative 3/2. But for this guy, this is a function times another function, going to be the product rule again. F of x is 1/2 ln x. F prime of x is 1/2 times 1 over x. 1/2 times 1 over x is 1 over 2x. And g prime of x, we just use the power rule, is negative 1/2. Whoa, I can't write negative 1/2. Negative 1/2 x to the negative 3/2. So the product rule then, well, we use the power rule in the first part to get that the second derivative is negative 1/2 x to the negative 3/2. And then the product rule, derivative of the first, it's 1 over 2x times the second, x to the negative 1/2, plus the first, 1/2 ln x, times the second, negative 1/2 x to the negative 3/2. And we will then just simplify this a little bit. This gives us negative 1/2 x to the negative 3/2. This becomes 1/2 x to the negative 1 times x to the negative 1/2 right here. So that also becomes 1/2 x to the negative 3/2. Oh, minus 1/4 ln x times x to the negative 3/2. Why am I getting so excited? Because we're subtracting something and we're adding the exact same thing, and our second derivative is actually kind of nice. 1/4 ln x times x to the negative 3/2. Or again, if you want to write it in this form, negative ln x over x to the 3/2 like this, or the square root of x cubed. All of them are good formulations for that second derivative. So let's type that into Desmos, negative 1/4 ln x, x to the negative 3/2. Call that h of x. Negative 1/4 ln x times x raised to the negative 3/2. That's going to be our second derivative. No spoiling it for now. And now we can look at concavity. So we need to solve this equation for 0 because this is a continuous function on our domain. And so the only time the concavity can switch is when it equals 0. That's the intermediate value theorem. Okay, so let's find when this equals 0, and then we can find our concavity. Let's use this form to find when it equals 0. That'll be a little easier. Again, we don't have to worry about when it's undefined. So we can multiply both sides by the LCD. That's just going to be when negative natural log of x equals 0. Because it's just going to equal 0 when that numerator equals 0, the denominators will cancel. That's when the natural log of x equals 0. Convert this into exponential form to get x equals 1. All right. So what we've got here is now we know from 0 to infinity, that's what we care about. That's our domain. The only place the concavity might change is when x is equal to 1. So everything in this interval will have the same concavity. Everything in this interval will have the same concavity. Let's look at the sign of the second derivative and the concavity. So you can pick anything in that interval and look at the second derivative sign. I'll pick 1/2. Why not? So I'm calling our second derivative h. Second derivative at 1/2 is positive, which means that in this entire interval from 0 to 1, it should be concave up. And if there's any critical points in that interval, it should be local minimums, local minima. So let's go back and make sure and check that it was indeed a local minimum in that interval. Great. If they were not, that would be a dead giveaway that something was wrong. And let's check something in the other interval, something bigger than 1, maybe 2. It's going to be a negative second derivative. So everything's going to be concave down here. Okay, so we can answer part C. It's going to be concave up on the interval from 0 to 1. And it's going to be concave down on the interval from 1 to infinity. And that also answers part D as well. We have a point of inflection where it changes when x is equal to 1. What's the y value? Y value is going to be 0 here. Right? If you plug in f of 1, it is indeed 0. So I believe we've done everything except for sketching the graph, but let's check. What does the problem want us to do? What problem are we doing? Yay, here we go. Intervals of increasing and decreasing, check. Local extrema, check. Intervals for concave up, concave down, check. Inflection points, check. Sketch the curve, that's where we're at. You are here. So let's do that. We're only looking on the interval from 0 to infinity. That is our domain. And I want to figure out a nice scale that makes this look nice. So what do we have? We have something going on at 0. We have something going on at e to the negative 2, which is pretty small. Something going on at 1. Okay, so really all the interesting stuff is pretty early on. So let's have 1 be pretty big. Have this be 1. This be 2. Okay. So it's increasing up until e to the negative 1/2, or e to the negative 2. What is e to the negative 2? Well, we will need an approximation now. E to the negative 2 is about 0.135. So each one of these is 0.2. So e to the negative 2 is like hereabouts. All right, so it's decreasing until then, and there's a local minimum right there. And again, the local minimum is negative 2 e to the negative 1. That's going to be our local minimum value. Negative 2 e to the negative 1. Sorry, negative 2 here is the negative 1 is negative 0.736. And before deciding the y scale, let's figure out what f of 2 is as well. just to get a little bit more information on the sketch. F of 2 is about 0.980. All right, so we can be pretty zoomed in on the y as well. We can be consistent then. Let's have 5 boxes be 1 and 5 boxes be -1 as well. So the local minimum is at this x coordinate over here, and a y coordinate of about -0.736. That's about 3/4, about -3/4. Oh, but it's split up into 5. This is 0.6, this is 0.8. So 3/4 is around here. This is our local minimum. All right. And then we also know that there's a function value around here. So we know it's decreasing until the local minimum and then increasing afterwards. It's decreasing here and then increasing everywhere else. What else do we know? We know there's a point of inflection at 1, 0. Point of inflection right here. And then it's concave up to the left. So combining both things, right? If it's concave up to the left, it'll look like this. And concave down to the right, it'll look like this. So what we kind of expect things to do then is, let's look at the other endpoint, right? I plugged in 2 to get an idea of what it's doing on the right. The other end would be 0, but 0 is not part of the domain. What happens as we get really close to 0? 0.1 is about -0.7. As we get closer to 0, -0.4, closer to 0, closer to 0, closer to 0. What's happening to our function as we're getting closer to 0? The limit of this function value as x goes to 0 from the right looks to be about 0. So we're going to have a big open circle right here. Now decreasing, I want to do this in a different color. I want to make it a little clearer. Big open circle, local minimum, inflection point, and then this is nothing. So we start here, decreasing concave down, local minimum, now increasing concave up, and now it turns to become concave down again. But it's still increasing, right? So it never starts decreasing, it's increasing everywhere here. This is our guess. And just like all of our guesses, let's go back and make sure that we incorporated everything correctly. Part A, decreasing up until that critical point and increasing afterwards. Decreasing up until the critical point, increasing afterwards. We got that. We graphed the critical point correctly. We also said concave up until 1, concave down afterwards. It is concave up here. It is concave down here. I said concave down we usually think about as parabolas, but this is also concave down. It doesn't ever have to like turn into a parabola. Good, and a point of inflection we got as well. Let's graph it and see if it's correct. So just like before, when I graph it, let's make our scale the same first, right? We're kind of looking from 0 to 3-ish. And then the y-axis is kind of going from -2 to +2 or something. Oh, -1 to +1 even. We're really zoomed in. All right, I'm going to make the function show. So it doesn't look exactly, right? It doesn't look exactly like we guessed. But it has the same shape. So there's still an open circle right here. And then it decreases, has that local minimum. And then the point of inflection is kind of hard to see here, honestly. We would have to actually zoom out if we wanted to get more information, but that's okay. This is just a sketch. This doesn't need to be anything. Now let's get a little bigger. Wait, we might have to get a lot bigger to really clearly see that inflection point. Okay, so yeah, now you can see that it's concave down here, right? It is curving down. We really zoom out, it's curving down barely. Barely it's curving down, but it's curving down a little bit. All right, and that's this video. Let me know if you have any questions and have a good one.